Okay, well that doesn't really matter as long as I didn't miss page.
Yes, there are 4 sheets.
Oh,
there are 4
cool.
sheets. And I already did a lot of the second and third page.
Okay, well tell me where you'd like to begin.
Actually, for me, the concavity isn't really the main problem since I understand it.
Okay.
I'm not quite sure about the statement 1f, like when the second derivative is blank, the curve of the concave is blank. I don't quite understand what he's looking for there.
When the second derivative is negative, the curve is concave down.
Oh, is that what he's looking for?
I also could say when the second derivative is positive, the curve is concave up.
Concave. Oh, okay, okay.
That's the best way to determine concavity is with the second derivative test, I think.
Right.
Right. Okay, is there anything else on this first page we need to talk about?
No, I can get the first page since it does go step by step. It babies me through. The 4th page, have I done that sketch correctly?
You must mean...
Not the 4th page, the 2nd page, sorry.
Okay, is the sketch, it's based on problem 4 only?
Yes.
Okay, so this was based on a original function from earlier?
Yes. Can you see the sketch that I did?
I can. And this is the function x to the 4th plus 6x to the 3rd so far?
Yes.
Okay. So that's our function. Let me just go through 3. Okay, so where is it concave up? Where is it concave down? So we're going to take the second derivative and figure out where that's positive. It's concave up in that interval. We're going to take the second derivative, figure out where that's negative. It's concave down in that interval.
All right.
Okay. Now, so I assume that when you took the second derivative, you got this.
Yes.
And we factored that into x plus 5 times x minus 2.
Right.
Okay, and then we made a sign chart, and we plotted points to the left of minus 5, in between, and to the right, and we determined that it was concave up when x is less than 5 or greater than 2. It's concave down when x is between minus 5 and 2.
Right.
And if we look at your chart, that's exactly what it looks like. It looks like we've got concave up to the left of minus 5. We got concave down in between minus 5 and 2, and concave up to the right of 2. So, yeah, that is correct. And we can't really put an axis on that. We don't know where that's located vertically on an XY plane.
Right.
Because there's a plus C that could be anything, and that would cause it to vertically shift. So it's all we know is the shape of the curve. And yeah, that looks correct. Let me just read the instructions here. Okay. Yeah.
All right. Then the main thing that I would have trouble with is on the very last page, since although it's review, it's stuff I'm not good at.
Okay. You know, I've been having you actually had 3 students this week that all got new iPhones for Christmas. They all took pictures and sent them to me, and they were all a little blurry. And I've been having discussions with my son, who's a computer expert, trying to figure out what's causing it. And he thinks that you're just not holding the camera steady enough.
No, when I look back on my pictures that I took, they're in excellent quality.
Yeah, I don't get it then. Because I actually had a student yesterday that did the same thing you did. He took a picture, sent it to my phone, and then I had to forward it to my email, and it came out blurry, and I thought that might be the difficulty, so I had him send the same picture directly to my email. Came out the same blurriness.
Yeah, since the pictures that I took, when I zoom in, it's perfect quality.
Really? Wow.
Yes, I can see it perfectly. Maybe
I do notice that as I zoom out on the pictures that you sent me to my phone, they actually become more readable. And so that's what my son and I decided is that you're looking at it in a zoomed out mode on your phone, and so it looks very clear to you. So I'm a little befuddled by it.
So how do the data, the better quality? Okay, send that again. Hold on, my mom is going to have me send it again so that way we can see it.
Send it to my email directly,
right?
And then we'll take a look at it. And I'm not sure what the Apple does. I was looking on my Samsung, and if I look at the settings under camera mode, there is a normal, a fine, and a super fine. I'm not sure what the Apple offers you in the way of those settings, but set it on super fine if you have an equivalent setting.
Hold on, I'm trying to figure it out.
The settings usually look like a gear wheel.
Yeah, I know what it looks like. I just...
Okay.
Picture, go picture.
Mm.
No, go picture. Here, camera.
It's an... Right? No, it's in excellent quality.
No. That. What? And
oh! That's
and
the
the
thing.
mail.
Oh, okay.
Yeah. And the mail.
Okay.
And ask.
Alright.
And then asking a size.
Yeah, let me open up my email again.
No, don't send. Yeah. Large size.
Okay, here, let me grab.
Is that better?
Hold on,
Check the rice.
I'll take a look here. It usually takes a minute or two for them to get received.
Yeah.
Okay, here it is.
I didn't realize you can do that. Sorry, it's the later one. I accidentally...
Which one did you retake? Just the 4th page? Image 5? In other words,
yes.
did you just retake this page here?
Yes.
Okay. Let me just take a look at image 5 then.
You can see.
Alright, let's have a look at it. Wow.
Is that better?
It is not. Hold on, let's maybe I didn't open up the right one.
Not better.
Huh.
What?
It's peculiar.
Then you're taking pictures.
We can make do with this because you can tell me if I can't read it.
But how to be focus and picture.
Oh, it was in focus.
Okay.
No, Mama, look. See this? Excellent quality.
Okay.
Perfect quality.
Okay, send the largest one.
I have. Anything more?
Go picture.
I'm a bit puzzled. I'm not quite sure what the answer is. Maybe I can figure it out. It may be on my end, perhaps, although I'm not sure how it could be on my end.
No, you're not.
Yes, I did. I checked it on the largest size, remember? The largest, it was like the 9.4 megabyte. That was the actual size. It was still the largest size.
Do you know what your pixel quality is on your camera? Is it 8?
I don't know how to check that.
It's probably 13. I think Apple's are, it's an Apple 6?
Yes.
It's probably 13 megapixels, which should be absolute crystal clear on my end.
It's crystal clear for me,
Yeah,
but
I don't get it. I don't get it. I'm not sure. Let me talk to my son a little bit more, because I could show you tons of stuff that people have sent me that come in pretty crystal clear. So I've never had this problem until this year, until the new year. And it seems to only be with people who have gotten new iPhones. So I don't get it. But let's not spend this session worrying about that.
Right.
Let's look at some of these problems. Okay,
Right.
number 5,
So,
that looks like you know how to do the first derivative pretty easily.
oh, the last page, the very, very last page. I don't know why it skipped image 3.
Now see, I got an image 1, 2, 4, and 5. Let me open up image 4. Is this the one you want?
Yes.
Okay, good. You know how to do 7?
Yes. I also know how to do 8, but 9 and 10 are the ones I'd have trouble with.
Okay. Let's talk about integrals, number 9. Integral.
I know how to do them. It's just doing them is
Okay.
an issue. Like, I somehow mess it up.
Well, first of all, let's talk about taking the integral of sine of 5x. Just something like that.
Right.
We're going to take the integral of sine of 5x, and then we're going to divide it by the derivative of the inside. Okay? So the integral of sine of 5x is minus cosine of 5x, and then we're going to divide by 5. Now, I know that's the right answer because if I take the derivative of that, I get that. And that's how you know you've integrated it properly, is if you can then take the derivative of what you got and you get the original integral. Okay? Now, this works only if this is a constant. So if I'm integrating any trig function and I have a constant multiplying my variable, then I can merely just divide by that constant. Same thing for something like this. Well, the integral of e to the 2x is e to the 2x divided by the derivative of the inside 2. So whenever you have these kind of functions, that's what you can do. Okay?
Wow, since he's always had us do u substitution for this.
Yeah, this isn't, well, okay, you could use u substitution for this, and it would result in the same thing. But
I've just never seen it like that. So wow.
yeah, it's actually pretty straightforward as long as you just have a constant. Now, in this problem, the very first thing I can do is remove the 5. You can always take constants outside the integral. You just can't take variables. Okay, so now what's the integral of cosine 3x?
Sine 3x over 3.
That's it. It's as straightforward
Plus-
as that.
Plus c.
Plus c. So there's your answer. Now, if you want to check your answer, notice that when we take the derivative of that, when we take the derivative of this part here, we take the derivative of the sine of 3x, and then we multiply it by the derivative of the inside using the chain rule, and that gets rid of that 3. So we end up with cosine of 3x times 5, which is what we started with.
Oh. Did not know that.
Yeah.
Since instead...
And I could have used U substitution to show you that, but when it's that straightforward, in other words, whenever you have a trig function of a constant times x, it's relatively easy to do without invoking U substitution.
Right.
There's a lot of functions that are kind of like that. In other words, if I want to integrate sine of, let's say I want to integrate the square root of x squared plus 1 all times 2x.
Alright.
Okay? Notice what we're looking at here. We're looking at the product of this times this, and the derivative of the inside is 2x, which is this.
Right.
Whenever we have this, we know that, well, if I let u equal x squared plus 1, then I'm going to end up with du dx is 2x, so du divided by 2x equals dx, and I'm always going to have the derivative of the inside in the bottom, which is perfect because that's exactly where I need it in order to take care of this 2x. In other words, when I convert this to u substitution, it becomes u to the 1/2 du over 2x. With that 2x, the 2x's cancel. Now I have a perfect integral in u. But
Right.
so one thing, in a lot of classes will not even teach this problem as u substitution. They'll say you use the power rule here.
Yeah.
Okay? So, and what we need to be able to use the power rule on something like this is where this function is f of g of x, and this function is g prime of x. So whenever you see that, whenever you see an f of g of x times g prime of x together, you know that it's going to be u substitution.
Yeah.
We had a problem last week that we didn't quite get to, where we were supposed to do this one. Remember it?
Right.
This is perfect u substitution. The question is, do I make the numerator u or the denominator u?
The numerator, since the denominator is always...
No, you make...
sorry,
I'm going to make the denominator u.
Right, the denominator, because cosine goes into sine.
What I know is going to happen when I let u equal cosine of x is that I know I'm going to end up with sine x in my denominator when I differentiate this. In other words, du dx equals minus sine x, which makes dx equal to du divided by minus sine x. Okay, so now when I substitute for dx, I'm going to end up with this sine x in the denominator, which is perfect because it'll be canceled out by that sine x, and I'll end up with the integral of negative 1 over u du, which is easy to do. The integral of 1 over u is natural log of u.
Right.
So what you're looking for the classical u substitution, and not all u substitutions are like this, but the classical u substitution is where the derivative of u is currently in your numerator. And that's the case here. The derivative of cosine of x is sine x. It's minus sine x, but we don't care about the minus. We can handle that easily enough. But the fact is that the derivative of this will cancel out with that, and it'll give me an integral of u. The whole trick is to be able to turn it into an integral of u without any x's still there.
Right.
All right, so if we look at 10, let's see, this looks like, you know, the quality of these pictures are just enough that I can make them out. So it's not really a problem. As long as I can read them, that's all that matters. I do think there's something strange going on, and I'm not sure what it is, but maybe at some point I'll figure it out or we'll figure it out. All right.
Something along those lines.
So the integral of the sum of two things is equal to what? The sum of the integrals.
Right.
So I can turn this into the integral of x dx from 0 to 7 plus the integral from 0 to 7 of cosine of x dx. And now it's relatively easy to do. And this principle is actually extremely important in calculus. If you can have a function that is being nothing but added or subtracted, it's very easy to integrate it. What's tough to integrate are things that are being multiplied. In other words, if I give you x cosine x, that's not so easy to integrate.
Right.
But if I give you x plus cosine x, I can separate it into two integrals, and then each of these is quite easy. What's the first one?
The first one would be the integral of x dx. That would be 1/2 x squared.
I'm going to evaluate that from 0 to 7 plus, what's the integral of cosine x?
Sine of x.
And I'm going to evaluate that from 0 to 7. So what do I've got? I've got 49 halves plus sine of 7 radians. And in both cases, when I apply the lower limit, it's 0.
Okay. Right.
In both cases, so I can ignore that. So there's my answer. Now, answer exactly and then round to the nearest thousandth. You just have to look that up in your calculator. Make sure.
Wait, I also have plus c, right?
No, because this is a definite integral. You only have
Okay, so
plus
there's...
c when it's an indefinite integral. And the reason being is that the plus c's kind of cancel. In other words, if I have a plus c there and a plus c there, they get taken care of by the evaluating it at 7 and 0. But you only have a plus c when you're dealing with an indefinite integral, not definite integrals.
Oh, okay.
Okay? All right. We just got a couple of minutes. You have any questions?
No. Since I can find the period, I know what the Fab 5, as he calls it. I can do
So you
derivatives.
understand the sinusoidal function?
Yes, I do.
Okay, good. And as far as integration goes, it looks to me like the only thing you've integrated is using the power rule and using U substitution. There are a bunch more integration techniques. I wish that it was like differentiation. Unfortunately, integration is the differentiation as chess is to checkers.
Right.
It really is. It's so much harder, it's unbelievable.
Great. I'm not good at chess.
Well, I'm not a great chess player either, but I know that chess is a whole lot more difficult than checkers, and so is integration over differentiation. And it's primarily because it's so difficult to integrate products. In other words, to integrate something as simple as x sine squared x
Right.
requires integration by parts. And you'll get to that at some point, I suspect. I'm not sure how far they'll take you into calculus in this class you're taking. But there's integration by parts, there's integration by partial fractions, that's a 2-week subject. There's integration by trig substitution, that's a month-long subject. There's integration by infinite series, and that might be a 3-month-long subject. So it gets progressively difficult as you work with each technique. And there are functions that cannot be integrated. I mean, they can be integrated, but there's no antiderivative. If I look at this function right here, you cannot find a function whose derivative is equal to this. Doesn't exist. So the only way they can integrate something, a function like this, is by converting it to an infinite series, and then infinite series are the sum of a bunch of things. So you can integrate each thing and come up with an approximation for it. But that's the truth about integration, is there's a lot of functions, and they don't have to be all that complicated before there is no antiderivative to it. Yep. But that's what makes it fun. That's what makes it challenging, for sure.
Yeah. Definitely challenging.
Okay. Do you use the recorded sessions at all, Diane?
Yes,
I'm going to send you a new link that I would like you to start using instead of the one I sent you after the last session. I'm just going to send you directly to my YouTube channel, and I'll send you an email of it as soon as I get this thing processed.
All right.
It's more direct for you, and it eliminates some of the problems I've had. Sometimes my web server isn't available for me to put the file on there, so it'll be better for you to be able to view it from my YouTube channel than from my web page.
Okay, I can do that.
All right, sounds good. I will talk to you next Thursday.
Yes. Thank you.
All right, have a good week. Bye-bye.
All right, you too.